Well, yeah, that's the same thing. What my answer was you make a business list plus kind of bring the first setup. This is you make a graph and structure. And this is finance for
Oh, no.
where you see there's that just started from the second one. So you just go through the second one.
Oh,
You
yeah,
just say,
nice.
oh, so you go from here to here. And here to here. And here to here.
So I too have like points of graph as a classes project and
Oh, shoot. Yeah.
oh, I see. Because if there's two like histories that are very similar, they're going to cross into each other in the graph.
Yeah.
Oh, I see. That's
Yeah.
actually
What do you do? And also it kind of helped out with the graphs for the past one. And that one was like, who was this? The first one was socialist. But then,
that sounds like
It's like almost time to start, but there's hardly anybody here.
yeah, that's a good one.
you could just start. Go ahead.
Last lecture.
Is there like, is there some, what's that?
Last lecture got
Got it, that's right. Good scan generative models. While we are waiting for a few more people to start, or get here before we start, so I've been wondering like what to do for the last couple of weeks of the course. This is kind of, like in some sense, it's kind of free time. Like we've done all the lectures around homework and like what I think are like the basic techniques in neural networks, modern neural networks, and so from here we have, so like the way the schedule originally was put together, we would take a whole week with like autoencoding and manifold learning, and then a whole week with generative adversarial networks. But given that that Alessandro did kind of like an intro to it all, and then I did pretty much, I did like a whole week's worth of stuff yesterday, and I think I have basically like a whole week's worth of stuff today. We have basically like a week free in the course. So there's a couple things that we could do. So I was planning on doing like kind of a deeper dive into neural translation models, so like the stuff that powers, Google Translate and things like that are pretty cool uses of recurrent neural networks. And that we sort of missed it because of the day off of school and my missing some of the lectures. So we didn't do that. We kind of missed that entirely. And we could do that, or really we could like do other things that maybe you guys are interested in that I don't already have on the syllabus. So coming up, it's like an introduction to reinforcement learning, which is a really popular topic. Not something that I'm super familiar with, but that doesn't stop me from lecturing on it. But that's already on there, so the plan is to do some of that. Anyways, I guess I'll throw it out there to you who so faithfully came on this day when not many people did. Are there particular topics where people are like, man, I'd love to hear this? Let's see, go ahead, anybody shout it out.
Yeah, I would like to do the deep reinforcement learning.
Yeah, so that's already planned.
Okay, so we are going to do that.
We're going to do that,
Okay.
so make sure we'll do that, yeah. Go ahead, Jake.
I'd be interested in hearing more about imitation learning tactics, like data set aggregation.
aggregation or augmentation?
Data set aggregation, Dagger approach.
Dagger? I don't know.
The idea of like trying to train a network when you're not sure how good your reference policy is.
So this
So
is
you have some
reinforcement
error in
learning?
your labeling, and you're trying to train something to kind of find a local minimum in that realm.
Okay. And there's a particular approach that you know about called Dagger?
Yeah, that's I just heard about it, done a little bit with it, and I'm interested in learning more of those techniques.
Good. Well, let's write this down. So there's a definite like star reinforcement learning. There's something that's like learning in the like presence of like or lack of confidence of your labels. Is that kind of like the general topic? In labels, and there was a technique called Dagger.
Yeah.
Okay. That's another thing. Who else wants to throw something out there? Go ahead.
What do you have on the remaining of the list, like the OpenAI stuff with AlphaGo, AlphaZero?
Yeah, so that's kind of wrapped into this URL.
And then taxonomy and also the translation, like C2C stuff.
Yeah.
If we like do more stuff on this board, are we gonna like replace some of these things or just keep all of them still?
There could be some possible replacements. Yeah, that's right. So I think this is we won't replace this. We'll do this.
Well,
Other things could be replaced.
then my vote is probably like keep everything and add more and not replace it.
Well, we can't keep everything and add more. We can keep everything. That's another thing. So that's like a vote. Keep everything. So the keep everything really is to just like replace. Like next week we would do like the seek to seek models. Yeah. So the keep everything means seek to seek. So this is diving deeper again, like we said, into neural translation and how you translate from one language to another, and how that's done, like how that was done just a couple years ago with lots of data, and how they do it now with just a little bit of data, which is pretty cool stuff. What else? Anything else? Any other topics out there?
This might be a little out of scope of what like we're intending to do, but I think it'd be really interesting to spend like a day or so learning more like meta, like how you do these projects in industry, right? So like how you approach deep learning in industry, like
Yeah, I thought about doing
how you build stuff like that. Yeah.
So what do you have in mind on that? The trouble I have with that is like it's pretty broad. Like
Yeah.
I could give you an example, but maybe that's not great because there's so many different ways to do that. But I'll put it up here. So like industry how to something like that. You want to say anything more about that? Like what you're thinking?
Yeah, I totally agree with you that it's broad, right? Like, and you'd have a better idea of what encompasses it than me. But what comes to mind is like several examples might be helpful, right? Of these topics actually applied in industry, right? But I don't know. Yeah.
Okay. Yeah. Fair.
I think I might be the only one. I think it'd be cool to like talk about how like Google or other machine deep learning entities do like self-driving or autonomous like motion. You know what I mean? And maybe that's just me not seeing.
So when you say just motion, do you mean like more than just like self-driving car, or do you mean
Like
like
self-driving
robotics?
car, or like a whatever it is.
Yeah.
Self-driving, whatever, self-propelling.
Yeah. So that's kind of part of reinforcement learning, but like maybe more focused on self-driving. So again, this is like definitely something I'm aware of and kind of know how it's done, but like I've never done it or have I really worked with anything like it.
Sure.
But that doesn't prevent me from lecturing on it. Any other ideas? Yeah.
Well, are we going to do more about attention?
Yeah, so I think attention's a really good option here. So like the last week I had this sort of like multitasking, which I was thinking about doing maybe like half attention, half multitask, because like they don't really go hand in hand, but they kind of do. Like, so I was already kind of thinking about putting some like intention models in there. But anyways, yeah, attention. I mean, like a really interesting thing to see would be like how are transformer networks using attention to basically replace your current neural networks, like get similar or state-of-the-art results. I think that's really quite interesting. It's kind of kind of a deeper topic in neural networks, like how do you get neural networks to use their capacity to do specific things. Anything else? These are good ideas. Another one.
Yeah, I'd also be interested in learning more about like hyperparameter optimization and meta learning.
Yeah. Yeah. So you said meta learning?
Yeah, like meta learning or just like other techniques for optimizing hyperparameters.
Yeah. This is such a rabbit hole. 'Cause actually, I have some like interesting newer things here that we could probably a little more unified. This is really just like brute force. So like I guess that's like maybe the opposite of rabbit hole. It's like actually not that interesting. It's like just do it. There's some like theoretical things that are interesting for like it's like really like operationally technical and not very like neural networky technical, but maybe interesting. And definitely like useful. Like if you're really gonna go do this for real, like yeah, that's a good idea. Okay.
And could we talk about an industrial practice? Like how does the company actually get things done?
How does the what get things done?
Yes, the actual product, like your company, because they do things.
Yeah.
I know there's a.
Yeah. So this is like a second vote for like industry how to.
Okay. This one.
Industry how to.
Okay, sorry.
Yeah.
I can't remember.
No, that's okay. So we're two there. Okay. So these are all really good ideas. Obviously, we couldn't do everything here. I don't know if it's worth doing a vote or something. Maybe think about this during the lecture. Maybe at the end we'll have a vote and we'll see. Okay, cool. And if you think of something else to at the end, I guess you could throw in for that. All right. So let's get started on today.
Another.
Yeah.
And if you going to talk about industrial how to, and we also talk about the skills they need to participate in the industry.
The what? Sorry.
Skills.
Oh, the skills needed. Oh yeah, another rabbit hole. Yeah. Skills needed.
Like how if we want to take an internship and what we need now.
Oh, that's actually probably a good idea. And probably because I can give you some perspective on it, maybe like a typical professor or student. So maybe that's a good one too. Not very technical, but probably very useful. Okay, cool. So let's get rolling there. So we're going to get into part 2 of generative models. So last time, this is what we talked about. We remembered what it meant to do supervised and unsupervised learning. How supervised learning seems like a really awesome thing because hey, you don't need labels and you're really like trying to learn something absolutely essential about the data you're modeling, but it's as a result very hard to do because you don't have this clear signal sort of representing relationships between data points, like your inputs and outputs and things like that. But that's okay because there's techniques that seem to work in certain areas, and we started talking about that. We started talking about in particular generative models for doing quote unquote unsupervised learning, and these things were learning to basically like the basic structure here was to like encode your data and then decode it, and so you use the data itself as as the supervised variable. You just try to reconstruct the data itself, and in the process, you sort of compress your data into some lower dimensional representation that represented the important factors of variation that describe your data, and can by describing it, you can regenerate it. You can regenerate your data from these label descriptions. So we talked about like these pixel RNNs, NNs, and we talked about autoencoders and variational autoencoders. There's one more autoencoder that I think is worth mentioning that can be used for interesting can be used in certain situations. So sometimes you might be in a situation where you have noisy data, or you can expect to have corrupted data, maybe as like, part of some, I don't know. You can get corrupted data in some sense. You wouldn't get like image corruption like this, but for some reason, you might expect that you would be given some corrupted data that you'd like to basically like uncorrupt or like denoise. So some data that has noise in it, but you'd like to sort of notice that there's a difference between the signal and the noise, and just get rid of the noise part. So autoencoders are used, and there's lots of techniques for doing this, but autoencoders are one technique for doing this. And it's just a simple variation of what we saw already. You start with, your data and try to reconstruct it, but you actually add noise to it in some way. And that addition there is not necessarily meant to be like literally add noise. There's lots of ways you can corrupt an image or any data, any type of data. But you literally like do this. It's almost like a data augmentation. It's like you take your original data and you just noise it up somehow. And then you do this training through this sort of autoencoding. But instead of trying to reconstruct both the data and the noise, you just try to reconstruct the data. So it's learning to forget the noise that you're adding to this. And like here's an example, right? It's like you have your MNIST digits. You can add noise in them in some way, and then you're just trying to reconstruct them again. Trying to reconstruct these from your noisy examples. And yeah, it works actually quite well in settings where you have a lot of this kind of data. Okay.
I have a question.
Yeah.
You realize that for the autoencoded, we make images become blur. So how does when add noise, how does it really help? Doesn't it make it?
Well, so we're generating, so your example, so like this is MNIST, and this is like a lot easier to reconstruct, right? That's like kind of, So that's a good question. It doesn't, it wouldn't work, well, let me see. You can have these autoencoders be as like sophisticated as you want. So like, when you do variational autoencoding, you definitely get blurry images as a result of maximizing likelihood. But that kind of noise is different from like the kind of noise that I think you're trying to denoise here, right? That's not very succinct way or like a very maybe satisfying way of describing that. But there are definitely two different kinds of noise. And so like for instance, you could take images, you could blur them, and then you could try to decode them to their original unblurred. But you would, if you're using a variational autoencoder, you would still get blurry images. So there would be some resolution there that you wouldn't be able to get to do better than. But there are more sophisticated techniques that you could use that don't give you blurry reconstructions, and you can still use these kinds of ideas to like learn to denoise them. So it's like simple autoencoders wouldn't work, and even variational autoencoders wouldn't work necessarily for all the data sets possible here, like faces and things like that. But you could do more sophisticated things, and you can couple them with this denoising technique of like augmenting with noise, and should work. It's a good question. Okay, so far what we've tried to do is to like construct the likelihood functions. So like in the pixels, CNNs, we literally tried to explicitly learn the p thetas, the conditional ones that give us the full likelihood. And when we did the variational autoencoders, we wrote our likelihood as a marginalization over the hidden variables, and that was an intractable integral, but we had some ways of approximating it, We couldn't optimize it directly, but we kind of, we were able to just derive this lower bound, and that was sort of good enough for that technique. So in each of these cases, we're like basically trying to construct the likelihood and optimize it directly, or find a bound for that likelihood and optimize that bound directly. But what if we just give up on this explicit modeling and just want to sample? So all we care about is being able to sample from the distribution. We're not asking, give me a representation of the distribution. We just want an ability to generate data that would follow this, this likelihood distribution, or the data distribution. So there's different ways to do this, and what we're going to talk about today are GANs, generative adversarial networks. And we are not in this technique, and you've already seen a bit of this, and maybe you already talked about this, but it's important to note that we are not going to be learning directly to these distributions. We are going to learn to produce samples from these distributions. And hopefully I'll make that clear as we go, how that's done and why this is interesting and very different from what we looked at on Tuesday. So let's start talking about a little more about GAN. So the problem is we want to sample from this complex high-dimensional training distribution, and usually there's probably no direct way to do this. Again, like direct meaning we explicitly construct this complex distribution. All we have is like this large sample of the data. Yeah.
I feel like I'm slow to catch on to something.
Okay.
When we talk about density, we're talking about like probability density.
Yeah. Right.
Okay.
So like this. Yeah. So density and distribution. We're talking about like something that's describing the likelihood of like pixel arrangements.
Right.
For images to be, in our data set or not.
So in that last slide, when you said we want to be able to sample, but we don't know.
So we want to sample from the distribution.
But we don't know the distribution.
Well, so we don't know it in the sense that we don't have an explicit like function that if we were to give it the arrangement of pixels, it would give us the probability or the density. Instead, we're just going to be like, instead of giving us a value that is like the probability, it's going to give us pixels that are likely to come from this distribution. Yeah. Thanks for asking the questions. I think maybe hopefully that clarifies it for not just you, but other people. So the way generative adversarial networks work is instead of trying to sample from a complex high-dimensional distribution, we're going to actually sample from a simple distribution and then transform that to transform the samples that come from that to be samples from this complex distribution. So we can sample from simple ones. That's easy. There's lots of ways to do that already, but we're going to rely on, so I guess I'm jumping ahead. The question is, what can we use to represent this complex transformation? Guess what it's going to be? Neural network. So the very basic notion here is we're going to sample from something simple. Guess what we mean by simple? Guess what it's going to be? You know what it's going to be already. Yeah, it's going to be Gaussian. Actually, it might be uniform too, but usually it's like, Gaussian. And then we're going to learn a network that's going to turn that sample into like an image, for instance. So the question to ask yourself is how, just start thinking about it from this perspective. Like what does it mean to turn one distribution into another? Like even in simple cases, like what would it mean to turn like a uniform distribution into a Gaussian distribution, like a clipped Gaussian, since the uniform doesn't cover the full range or it's in a compact domain. This is kind of like this is the idea. Like how do you do this? It's actually a pretty complicated idea. If these are fairly simple distributions, you can do this. Like a very simple way to do this is to just map the CDFs, so the cumulative distribution functions for each of the distributions, to each other. So you can basically, the CDF is an invertible function, and once you have one, you can map that to the other one, and then from there you can get the probability distribution by taking derivatives, and like that. There's a pathway to doing that for things you can write down. But for complex distributions where you can't write these down, you can't compute CDFs explicitly, then this is like a much harder problem. So, not too long ago, somebody came up with an idea that was very novel and different, and was met with all kinds of acclaim. And Jan LeCun was like, "This is the most important thing that's happened in deep learning since last year." Yeah, but it's this idea of generative adversarial networks. So we know. So there are 3 words in GAN: generative adversarial network. So we know what networks are. At least you better by this point. We've been talking about generative, what that means. We want to be able to generate samples from this distribution. So what's the adversarial part? Well, that's what we're going to talk about next. So in GANs, you actually have actually there's lots of GANs now, and there could be lots more networks involved. But in what would be now called the plain vanilla GAN, you have 2 networks. I mean, these 2 things, in any GAN, these have to exist for it to be a GAN. But there's two networks. There is the generator network. That's actually the thing that's generating, that's taking the sample from the simple distribution and turning that into a sample from our complex distribution. That's the generator. But then there's this other network, and it's called the discriminator. And its job is to notice when data actually comes from our true data distribution, so from the actual data that we're training on, and when data is generated by our generator. That's what the discriminator is trying to discriminate between. It's trying to discriminate between the real data coming from our that we're training on. That's our actual data, and the data that we're generating. So it looks kind of like this. You have our real images from our training set. This is from CFAR or something like that. We have cars. And then we have this generator here, which is trying to take some simple multivariate noise and turn that into an image. And so that's what the generator network's doing. The discriminator network is then looking at these things and saying, "Oh, this is real, and this is not." And yeah, that's its whole job. Basically, it's like a 0 or 1. Is this real or is this fake? And this is like unsupervised learning in the sense that we're learning to generate and sample from distributions. But there's obviously supervision happening here. So the supervision is all coming from this discriminator network, which has the labels of this is real or this is not real. And we're trying to fool it. So here's how this works. Let's see. So in everything that we're going to be doing now, you're going to see D's and you're going to see G's. Okay? D's refer to the discriminator network. G's refer to the generative network. So here we're looking at a loss function for training a GAN. And there's 2 pieces to it, and there's D's and there's G's. So over here you see there's D's only in this term. And over here you see there are D's and G's. And over here, you see there's something saying like you want to minimize with respect to G's. So this is theta G, meaning the weights of the generator network. And this is saying maximize. You want to maximize this thing over weights of the discriminator network. Okay, so what's going on here? So we have two pieces. Oh, there's actually one more thing that's really important here. There's two expectations taken here. So log of some, so remember D is a probability, so this is actually log of some of probability, so this is a likelihood, and we're looking at the expectation of that likelihood, so we're trying to maximize that. So this expectation is taken over the data. This expectation is taken over our simple distribution that is generating, that we're using to as like the input to generate our fake data. Okay, so what does all this mean? Let's look at all this. So let's concentrate on this term right here first. Okay, so remember there's two things happening here. There's this generator that's trying to generate real data. Well, it's fake, but it's trying to look as real as possible. And there's a discriminator that's trying to tell the difference between the two. So the discriminator, in this term right here, this right here, so this is the probability that real data is seen as real by the discriminator, okay? So, like, this is, like, again, this is the probability that the discriminator thinks real data is real. We want this to be, the probability to be 1. We want this discriminator to get this right. We take logs because working in log space here is better, as we talked about in the past. But this is what this thing is trying to do. And notice that we are trying, so we want to maximize this probability. So that's why there's on this loss term, there's this max over theta d. We want to maximize this term with respect to theta, so that our discriminator is really good at getting the real data, at noticing the real data is real. However, we go over to this term, and this is again the discriminator, but instead of it being real data that's going into here, we take a sample from our simple distribution. It's like a multivariate Gaussian. And then we run it through the generator. So this generator is giving us some x. But it's not from the actual distribution. This is from this is generated. So this is fake. And what we want the discriminator to be able to do is to notice that this is not real. So we want it to assign 0 to these samples here. Okay? So again, maximizing this term with respect to the parameters of the discriminator network would mean that the discriminator is pushing its prediction to 0 on here. So get the real data right, assign it a 1. Get the generated or fake data right to the wrong word. Assign a 1 to the real data. Assign a 0 to the generated fake data. So the discriminator, that's all its job is to do. And you can imagine, like, when we first start training this thing, and there's like basically random weights in this matrix, in this network. But this is going to be pretty easy, right? Like, it's just going to be able to. There's going to be like hugely obvious statistical differences between the real data and then the fake data that we're generating, because it's just going to be like essentially random pixels. So this should be pretty easy to do. If we didn't have this minimization term here, this would be pretty easy to do, I think, right? Just starting from whatever random weights here, you would just try to maximize this term for the discriminator weights, and you could do this pretty easily. We learn to notice differences. But at the same time, we have we are also trying to minimize this loss with respect to the generator. So what does that mean? So again, the discriminator's job, if we just had like a fixed generator G, and especially if it was just like random weights or something, we should be able to do this really simply. This would look like a lot of the problems that we've already been thinking about. But we have this other thing that's happening, and that is the generator is trying to get good at generating real data. So what does that mean? Well, let's look at this again in the math. So there's no, in this term right here, there's no theta G, there's no generator here. So actually, as we try to minimize this term with respect to the weights of the generator network, this term is not affected. So this is like a constant with respect to that operation. So we can't change the discriminator's ability to get the real data right from this term in the loss function. However, we do have the generator here. So if you just think about this term right here, if we minimize, if we're trying to change the weights of the generator network so that we minimize this term, what is that doing? If we minimize that, where is the prediction from the discriminator going? Yeah, it's going towards 1, right? So the act of minimizing this term over here with respect to theta G is to fake the discriminator out, right? It's that the generator is using the feedback from the discriminator, saying like, you know, it's fake in this way or so, to then say, okay, I can adjust my weights so that I can actually look like more real data, right? That's what's happening in this term right here. So can't really do anything about the real data. Okay? The generator can't affect the real data, but the generator is generating fake data, and the act of minimizing this term with respect to its weights is to fake the discriminator out, is to make it think that this is real data. It doesn't do it through changing the weights of the discriminator. The discriminator at this point, I think of it as like fixed. Like once, you know, if that's fixed, then the generator is like, okay, I'll start from this point and try to like change the data, or change the way that I generate data so that it looks more real. Yeah.
Can you go by the other term of 1 minus t? Where I'm minimizing and maximizing, I'm kind of confused.
Okay, so I have these words up here again, and I'll say it one more time, and we'll do this until we're not confused. So this should feel really weird, actually, because in everything we've done so far, we've written down a loss function, and then we've either like minimized it or maximized it, right? Like all the weights that were there, like, you know, if it was like a true loss function where the loss of 0 was meant like perfect classification or perfect reconstruction, then like that's what our job was to do. But here we have something different, where we're trying to do one thing with one set of weights, and then do the opposite thing with the other set of weights. So this is not like anything we've seen before in terms of like optimization of this objective function. So going through this one more time, the discriminator wants to maximize the subjective, because when it's maximized, it's getting, like when it's absolutely maximized, it's absolutely maximized when it's assigning 1 to the real data, and it's assigning 0 to the generated data. So that's the perfect state for the discriminator. That's what the discriminator wants to do. It wants to tell the difference. But the generator, it's trying to fool the discriminator. So again, can't do anything about real data, but so it's trying to minimize this term, and this term is minimized when the discriminator assigns a 1 to the generated data. So the discriminator thinks it's real when it's actually been generated. Prince, does that get anywhere close to helping you? Yeah? Okay. But if it didn't, you can say so. Yeah, go ahead. Eric.
How How does the expected value fit in there? I get what's inside the log terms, that makes sense to me, but why the expected value of that? Oh,
Because we don't just have like one sample, right? This is like,
right.
so when we actually do this, we approximate this through mini batch sampling, right? So like we sample from our data a batch, and we sample from the generator a certain batch size, and that's giving us terms here to do expectations over, and then we'll do gradient descent from there.
So we want, like for example, the discriminator wants the expected value of both those terms to be like 1.
Yes, exactly. So that would mean
That means always identified.
yeah, exactly. That means like for almost all samples, which because we always have finite data, it would mean all samples. Yeah, we're getting this right. Exactly. Yeah, because it's over the whole distribution. Yeah,
So I think I'm understanding how this works, but it's not clear to me why you use this kind of network rather than just have like a fully connected layer with like 2 classes, just like 0 and 1, and have your label data just be sort of real or fake. Rather than trying to like base it on a distribution of a real image, can you just sort of have sort of a bunch of classes of like real or fake distributions?
yeah. I guess the trouble is that you don't. So you have labels for real, but you can't just say that all the other like irradiance of pixels are fake. Because if you just like slightly perturb some pixels, like you still have like an image that's coming from that distribution. It should still be assigned a high probability. So what you don't have is you don't have all the rest of the labels. Like so I guess like if you had like, if you had the distribution already, like if you already, you wouldn't have anything to learn. But what you have here is just like some large sample of it, and you know, all you really know is which is that this, your data, your training set is from the real distribution. So you're trying to maximize the likelihood of that as much as possible. But all the rest of the pixel arrangements that aren't in the training set, you can't say whether they're 1 or 0 or halfway in between or something like that. And that's a reason why you can't do what you're saying.
So, like in an example of this, your data can be like an ImageNet data set, and so you learn the manifold where all these ImageNet images live.
Mm-hmm.
But then, if you want to generate something, if you pick a point on the manifold, how do you know what class that is, or is it going to be like a combination of different classes?
Yeah.
Classes, so how do you generate?
Yeah, right. So that's a good question, a good kind of conceptual thing to think about. It doesn't know anything about classes, right? And like the manifold structure doesn't necessarily respect the class structure. That is to say that like the subset of all things in a class aren't necessarily like some connected subset of the manifold. Like there's no guarantees on that. Obviously, there are some arguments from continuity that like suggest that you should at least like if this image is from this class, then everything sufficiently close to it is also going to be from that class. But yeah, it's not. If you wanted to enforce, like you can enforce that kind of thing on top of this as well by having additional terms in your loss that would like say try to get at classification, everything like that in this sense. Well, yeah. So what you could do, and then there's actually there's like a couple of different architectures for GANs where. So again, Z is parameterizing this manifold. It's parameterizing the distribution. So you can force Z to say be aligned or correlated with class, or at least some of the dimensions in Z to be that way. So like there's a technique called InfoGAN that would allow you to do this, where you like maximize mutual information between some of the dimensions. In your latent space, so the dimensions of Z with things like the class. Or you can make your GAN class conditional. So you can actually like learn to generate like sub-manifolds within the like a full manifold that let's see. I guess it'd still be that actually that one maybe not solve it, but at least you would know. Yeah, you'd be able to generate from a particular class. So so you can make these things conditioned on the class, and so it will generate not just an image on the manifold, but an image in the class.
So if we did without these tricks, just using this vanilla version, then we pick a random white noise vector, and that would just end up being something that we can't determine.
Yeah. So like let's say that you also trained, you train another network that was a classifier. Then you would give that generated image to the classifier, and it would tell you what the class was. But you could also imagine doing that all jointly, although I'm not really sure how. Like I don't know if I've ever seen that, and that might be really tricky in this because this is not like a typical training scenario. But so I don't really know the answer there, but these are Legos. You can kind of put them all together, and usually you get something that doesn't work. But then everyone's found something that works. Yeah.
How can we show that after this mass game and the model is approaching to the chemical?
So you're saying this distribution after applying G that it's approaching like this distribution, is that what you're asking? Yeah. So how do you guarantee that you're actually converging to something like that? No surprise here. You can't prove that. You can prove certain things like for like a fixed generator, you can prove like what the optimal discriminator looks like, or what its optimal like prediction like its probability distribution looks like. But you can't guarantee that this is that G of P, so the distribution of the G of Z's. You can't guarantee that it's actually going to get there. But you can. But if this does you can't guarantee that it'll get there. But you can, let's see, what can you say? You can, you can't really guarantee that it'll get there, but it does get there. That's an interesting question, actually. I mean, the original paper shows, like when you play just one side of this game, what the optima are, and how that corresponds to like Nash equilibrium and things like that. But actually, you can't guarantee like in the gradient descent game that you're playing that you actually ever get there. So, yeah.
So how we guarantee that is always approach? Because in other words, you're always saying like our data is always like Gaussian. Because you take the random noise as a Gaussian and you're saying, this is approach.
What you're doing is you're actually transforming the samples from a Gaussian into samples from the actual from your actual distribution. So like if this works, like if you could get this to be where it's perfectly fooled by the generator, so meaning that like the discriminator was basically assigning a probability of 1/2 to to the reals or to the fakes, and just because it just can't tell anymore. Then, in the case where, let's see, I mean, you still can't guarantee it, but if you, let's see, what's the right way to say this?
Can I ask another question?
Oh, let me think about this for a second. I won't be able to figure it out. Like the answer is something like if you can still learn something from here, if there's still something learnable as you play the game back and forth, then you then you will converge to the like you will actually get there. So like I think the real question is something like it depends on the capacity of the network to be able to learn the transformation between this distribution and this distribution. So like there's a theoretical guarantee about being a universal approximators, these neural networks, and so there is a network that would allow you to make the transformation from one to the other. But there's not a guarantee that that playing this minimax game will actually get you there, because one, you may not have a high enough capacity network. Two, you might not have like a sufficient set of like sample from here. And three, this may not be sufficiently high dimensional to fully parameterize what you're trying to learn. So like there's all these things that are like making it hard for you to actually do this problem. And yet, you can still make it still work. I don't know. Also, do you have anything to add to that?
These like
You spend a lot of time with GANs.
yeah, especially in this period. GANs are just really hard to train in general, like it is known.
I haven't even gotten to that part yet. these are really hard to train.
Yes. But, I mean, we can do really cool stuff with this, but yeah, the fact that they play a game like against each other makes it really hard, because usually you reach the perfect discriminator before reaching the perfect generator.
Yeah.
And so.
And most research right now kind of pushes you in directions to prevent that from happening.
Yeah, you're basically just.
But even in that case, you don't know that you've gotten like the perfect generator. And it's like,
Exactly.
and the reason why you can't have theoretical guarantees on this is because of like the lack of relationship between like capacity of the generator, sufficient sample size from the actual data distribution, and like sufficient dimension of your simple distribution to be able to represent all the latent factors that would allow you to generate in your manifold.
But even just the fact that they are playing, like,
Yeah,
since
and
they are playing this game, like, you don't have a guarantee that you will reach the right generator, because, like, it was shown that, like, a lot of the time, the two reach a point where basically, like, they keep running in circle, basically. Like, I go, as a generator, I go one step forward, and so as a discriminator, I go one step back. And so the generator comes one step back, and the discriminator.
Yeah, I mean, if you think about it, what it means to be like, if you think of all these weights put together, like in one large. So instead of just thinking about it as like two different networks, you actually have one large network doing two different things. What you're looking for is you're trying to get yourself on a saddle point in this objective space. So your loss function, like the surface hypersurface I was describing, you're trying to put yourself onto a saddle point, and that means that like there's certain directions you could go where you would the loss would go down, and there's certain directions you could go and the loss would go up. And as a result of that, you're like not like when we've been doing all this other training, you're like trying to get to the bottom like of a well, but here you're trying to land yourself on a saddle point. Like that's just like dynamically, that's a really hard thing to do. Like 10 minutes ago, there's like a question over here. Who asked it? Was it? Okay, go ahead.
So I think the fact that they play the game is what get them to settle on perfect body for the generated.
So say it one more time. You're asking.
The fact that they play the minimax game.
Yeah.
Is what's enabled the system to get like a stable image where the discriminator says this is actually running, so it ends.
Yeah, that's right. I mean, the discriminator is trying to say, I can tell the difference. The generator then takes that, whatever it's doing to tell the difference, then takes that signal and says, okay, I'll adjust myself accordingly to make it so you're not as good at doing this. And then the discriminator says, okay, now you're generating like that, I can tell the difference. And then the generator says, oh, I can take that the way you're doing that and make it even better. So the basic mechanisms are like believable, I say it in English, but getting them to work in practice is pretty hard. So let me get into a little more of the details here so we actually finish today. So we really do play a game in the sense that when we're training here, we actually alternate between maximizing this, maximizing the objective function with respect to the discriminator weights, and then minimizing the objective function with respect to the generator weights. And notice that again, this term isn't here in this because this is just a constant with respect to the generator weights. When you take a gradient with respect to the generator weights, there's no generator weights there, so it's a 0. But what happens is, and this is sort of alluded to before, this doesn't work very well. In particular, this term right here is really problematic because when like you're just starting off and like the discriminator is really good at telling that this is not like this is fake data, your gradients coming from this term tend to be saturated, tend to be really shallow. So it's hard to make steps to improve the generator at first because it's just so bad. And the discriminator has like a much easier job. Think about it. The discriminator just has to like learn 0, 1, right? It's like that's really easy compared to take a multivariate sample and turn it into a real image. Like that's like these are when you look at the actual implementations of these networks, the generators are far more complicated or complex and higher capacity than the discriminators are. So, like, one thing that was noticed right away is if you just change this term, so instead of it being minimizing 1 minus this, you just maximize this, which, because this discriminator is between 0 and 1, it gives you, it's doing exactly the same thing. This would be fooling the generator, right? So, like, you maximize this term with respect to the generator weights. That would be assigning a 1 to the generated or fake data. So it's doing the same thing. If you just do this, it turns out that in this regime where the probability is low, or so where the discriminator is really easily discriminating between the two, you actually tend to have much larger gradients, so like the generator can learn more quickly. So this is like, it was just something that was noticed is the case, and right away, this was a technique that made it a little bit easier to train GANs. We already talked about this a bunch, or we alluded to it. It's really even after having done this, where you get some larger gradients. This is like learning can happen. It's still really hard. Because you are alternating between maximizing this and then maximizing this and maximizing this and maximizing this. You're shifting between the weights. Again, the way to think about it is there's really one overall loss surface for the combined set of weights of the discriminator and the generator, and you're trying to put yourself on a saddle point in there. And that's a really hard thing to do just in general. And besides that, you're like playing a game to do that. So instead of like trying to get yourself onto that manifold, like this side pushing up, this side's pushing down, this side's pushing down, this side's pushing down. So it's really hard. But when it works great. This is like pseudocode for how to do this. You think of this as like, so you run through your training data, you do case steps of the following, sample mini batch of noise and mini batch of real data, and then you maximize this with respect to the discriminator weights, and then you take a mini batch of noise from your simple generator, your simple distribution, and then you do stochastic gradient descent to maximize the weights there, or maximize the loss with respect to the weights there. And this is like another sort of hyperparameter thing. So you had this choice of like how many steps you're going to take optimizing the discriminator before you optimize the generator. And like some people say, hey, just do one step, you know, do one update here, then do one update here, and so forth. Other people say do more of the discriminator. I mean, again, like the rabbit hole of hyperparameter search is like one of those hyperparameters that's just a mess. Yeah.
So since it's more difficult for the generator to do its job, wouldn't you want to update the generator more?
Well, where does so like you're thinking right, but the only signal that the generator really gets to use to update itself is from the discriminator. It's how well the discriminator is doing. So the discriminator has to be doing well for like it has to be able to actually discriminate between the two for it to give any meaningful signal for how the generator should change itself to look more real. So like the discriminator has to be good enough. So you actually, you know, you tend to bias this training towards the discriminator so that it can give signal to the generator to update itself. Because again, the generator, like, there is no labels here. The only labels we have in this whole thing is this data comes from the training set. So it's sort of unsupervised, like in the same way that variational autoencoders or autoencoders were unsupervised. You're just using the data itself rather than like having some external labels. But this is just using this really clever way of providing feedback. Is that a question?
Well, I can ask, in what, when can we expect leadership easily?
When is it easy?
Yeah. When is it
Turn a simple distribution into a simple distribution. It actually works great. It's really, as you can see, easy thing to do. It's a fun thing to do. You should have been part of the homework, but I didn't do it. But yeah, like you can use these techniques to turn like a uniform distribution into a Gaussian distribution, like one dimensional to one dimensional. Actually, it works pretty amazingly well.
What was the first thing that you did?
Yeah, this is actually what inspired. Like I guess like the lore around this is like Ian Goodfellow and some people are having beers, and it's like, how would you do this, you know? And like they're like, I don't know. And then they started thinking of these ideas. I don't know if it was really over beers. That was more.
If we replace the data to say simple multivariate Gaussian distribution, and after this process, can we approximate this Gaussian distribution?
Yeah. Yeah, because like that's your data this time, right? Like if it's from a Gaussian, then yeah. That's what I'm saying. Like you like pick two like parametric, easy to understand distributions, make sure they're different from each other, and then learn and then do this. It actually works great. But like the thing is, like we're trying to like generate images. That's way hard. For a lot of reasons. In particular, like, is there really a distribution? Like a nice, like well-behaved distribution that's describing, you know, natural images? Is there a way to measure that? No, we just use our eyes. The eyeball metric. Okay, so yeah. Once this is done and this works, then we can just use our generator network to just generate images from our latent space. We just, literally, like I said before, you can just pick anything, any Z in your latent space, and generate something. And hopefully it looks good. So here's some examples. So where it works well, like in these simple distributions, so it works, so something that's a little bit harder, but not much harder, it works great on MNIST. These are all generated from this simple GAN, like this plain vanilla GAN implementation. And then this, what it's showing here is like, for this last row, what are the nearest actual real data samples that are, you know, that are most similar to these generated ones? You can see, like, you know, you can't tell the difference, right? I mean, just this is learned to do this really, really, really well. Here's something from a Faces database. So these actually look way crisper than if you were to use like a variational autoencoder, although these are still not quite that crisp. But again, you know, like it's generated, so like again, like if you take this column here, each of the samples in this column is the real data that's closest to this one. You can see that again, it's pretty close. There is some blurriness, but it's better. You can generate again CFAR images. These are better than the variational autoencoders, but I would say not much better. And you might be wondering about that. because like I've been showing you pictures of like GAN generating like super crisp, high resolution faces. So like, where did those come from? They didn't come from plain vanilla GAN. That's the answer. Yeah. So I think we're just gonna. We don't have tons of time left. So let me just. Yeah. So like, what do the architectures look like here? You have to do. You're going from a vector, something that you sampled from your like multivariate Gaussian, and you have to turn that into a multi-channel spatial extended image. So you're going to be using convolutional networks, and you're going to be using transpose convolutions. That'll let you go from smaller spatial resolution to larger resolution. So this is, this isn't different from what we looked at when we were looking at transpose convolutions. This is like when we were looking at what we were doing at that point. It was that long ago, and I taught it. I don't remember what it was we were doing when we were doing transpose convolutions. Shoot. Maybe it'll come to me. Doesn't really matter. This is what we're doing. So, yeah, just that's maybe you were thinking that, like that had to be the case, but this is how it's done. So this is why these are really, really, like, these are complex networks. It's trying to take just a few numbers and turn into like a very large number of entries in this image. So like, this is something called the LSUN data set. I don't know how it became like one of the things that they did with GANs, but like, there's pictures of bedrooms. Maybe it came off of like, like a rental, or like a bunch of rental websites, showing pictures of what the house looks like on the inside. It's probably likely, I don't know exactly, but you can see that like, hey, the resolution's not all that great, but again, with these plain vanilla GANs, you can generate these things that look way more like bedrooms than, say, we've done with anything previous. And what's cool, again, so I want to warn you, like, you're going to see like a lot of images that aren't like super like pleasing to look at, like the ones that we're going to show a little bit later. They were generated by GANs. They're very amazing, but they're not exactly like, they kind of will make you squirm like when you look at some of these faces. They're like not exactly what you would expect from a face, but they're really close. What's cool about GANs is, I can take one point in my latent space, I can take another point in my latent space, and there's a whole line segment in between them. That as I move along that line segment, I should get, because this is mapping to some manifold in my image space, I should get some like nice smooth transformation from like the image that corresponds to the beginning of that line segment in Z, latent space and Z space, to the end. And this is showing that. Each one of these rows is showing you that. There's like, you pick like a beginning bedroom and an ending bedroom, and as we move along the line segment between those two, and we generate the image corresponding with those, you can see we get this like very smooth, nice transformation from one pretty bedroom to another. And that's pretty cool. So like, this is like a confirmation, at least eyeball-wise, that we're like learning some sort of manifold in this space. Okay, I warned you. Like, it's almost good, right? And like, you look at like, I don't know, a few of you are like, oh man, it's not quite right. But then like, you might meet somebody for real, and then, yeah. The eyeball metric has its problems. It's wrought with bias, unfortunately. But there's something very cool that actually happened, like just was noticed as a property that gets learned here. And that is like some sort of semantic understanding within the latent space. So what was done was to like take a bunch of samples of images that like had a common property. So in this case, there's a couple common properties: faces of women that are smiling. And then you find some other part of latent spaces, like these generated images, that again seem to be generating women's faces, but they're not smiling. And then look, we have another part of latent space that seems to be generating men's faces, and they're also not smiling. So what this is saying is that some of these factors in the latent space are corresponding to, say, like gender, they're corresponding to level of smile. Yeah.
Do you have any control over what it generates? Like, how do you tell?
In the plain vanilla GAN, no. But this kind of stuff often happens because this is like a very distinct structure that you need to know about to reconstruct images.
So are these like separate networks in this case?
No. This is all from the same network. This is just like different regions of latent space. So like here's a region of latent space that's generating women's faces with smiles, women's faces with neither smiles nor frowns, men's faces with neither smiles nor frowns.
So these are like picked up after the fact. It's not like they fed in a specific vector to like generate the face of the smiling woman.
No, right. Like out here, you don't know what that is. You just start looking at samples from different parts of latent space. You're like, oh, this seems to correspond to that. So it gets better than that. So not only is it like, does this sort of hold? Like you can kind of understand like what latent factors are being learned. You can sort of do arithmetic here. So like in this latent space, you can these latent factors have semantic meaning that can sort of be added and subtracted. So if I take if I take a bunch of samples of these that have this property and I take their mean, so I'm like somewhere very representative of this feature in my latent space, and the same thing here and the same thing here. If I take my notion of smiling woman, it's like the average of that, and neutral woman, neutral in the sense of like no smile, no frown, and I actually subtract the vector corresponding to smiling woman, or I subtract the vector corresponding to neutral woman from smiling woman, and add to that this average vector for neutral man. What do you think I get? You get smiling man. So this is the sample that corresponds exactly that one in the middle, exactly to the vector that you get from here. So this is a single vector latent space. Subtract this single vector, add this single vector. You get this. You get a vector latent space, and then this is the generated image for it. And then these are the things nearby. Just kind of like perturbing a little bit around it. It's pretty cool. So remember, like, think about this in terms of unsupervised learning. Like, you learn something. You learn like this vector space is encoding something, semantic about about images that we trained on. So that there's notions of gender, there's notions of smiling, and there's other notions like this. Like a lot of these had sunglasses on. So if I take my sunglass man, subtract off my no sunglass man, or I guess not sunglasses, just glasses. Glasses man, subtract off my no glasses man, add my no glasses woman, I get woman with glasses. So again, this is the vector, or this is the image corresponding to the vector that is exactly this, and then those are the ones nearby it. So you can see, like, there's another latent factor that seems to be, or there could be a couple of different ones, but like, another latent factor that seems to be learning something about glasses, like putting glasses on a face. And it corresponds to the degree of glasses. It's pretty amazing, actually. I love that. Again, there was no supervision that said anything about there's glasses here, there's even a person here, or there's anything about face. This was just all learned by in this adversarial way. Oh, by the way, that's why it's called adversarial. These two things are playing against each other. They're adversaries. There's the second. There's this explanation for the third. Anyways, turns out there's like all kinds of GANs now. This is like they're really fun and amazing, and people have done all kinds of great stuff with them. You could read forever on these. Just in the last couple of years, there's also this GitHub account, SoMyth, which is actually the person at Facebook who originally wrote PyTorch and did something called ostracized GANs, which are a big improvement on like the plain vanilla GANs. in terms of being able to train in a less unstable way. I wouldn't call it stable, but less unstable way. There's like a lot of good like references and papers there about like how to train GANs. Anyways, lots and lots of GANs. So there's just certain tweaks on GANs that allow you to get like much crisper looking images. Like these bedrooms, actually if you go through the images, there's like still kind of problems with them, but they're like way crisper. Like they look way more like real images. Again, it's always bedrooms. I don't know. I guess because like you think about it, so the reasons I think why faces and bedrooms, one of the reasons why they're used is like there's lots of factors within them that like we can easily sort of like describe, right? So like we get faces really well. Like we all are adapted to like understand what facial features mean, and like we can attribute that to like latent factors. With the bedroom, it's like there's windows and there's beds and there's chairs and there's walls and like we get all that, and we can hope to learn to somehow parameterize all that stuff. So anyways, there's like I mentioned Wasserstein GANs. Again, another technique for getting much crisper images. And then this one that we looked at the beginning of this semester that I think is super impressive is a group at NVIDIA did what are called progressive GANs. And this is like, they're called progressive because your generator like starts out kind of shallow, and then you train it like optimally, and then you add another layer and you train that optimally, and you add another layer, and you train it optimally. And if you just do this process, your GAN learns to like really, really generate like amazingly crisp facial images. This is from the Celeb data set. So just like a bunch of celebrities. So like they look like celebrities. Like I just love this because like if you didn't know anything about this and you just like but you like watch some TV, maybe you look at the internet every once in a while. Like you just would learn that like this is what celebrities look like, and it's really interesting too because it really shows like where a lot of our cultural biases are. Like these totally learned cultural biases right away, right? Because all it is they just have the data to learn from. So like if cultural biases in the data, like it's skewed toward like a race or gender or certain things, like it's going to learn to do that. Like it's just you can't help it. It's a statistical property. It's going to learn to do it. There's like way cooler uses of GANs. So cycle GAN is really amazing. So it's actually two GANs. It's two GANs in one. And what it's doing is it's actually the job here is you have two different distributions of things, and you want to learn to like map between them. So like you want to be able to like learn how to take the properties of this distribution and map them over onto this distribution and vice versa. And so you have basically like these two GANs with a reconstruction loss for going all the way around the cycle, which is why this is called cycle GAN, which allows you to do crazy things like turn horses into zebras, and turn like summer or like winter pictures into summer pictures, and like turn apples into oranges. Like that's kind of funny. There's lots of cool examples. This one's I think really pretty fun. If we had time, we could play around with this. If you have never done this before, go do this and like perturb the cat picture until like you get like this mutant cat. But what it's learned to do is it's learned to generate from like a simple sketch like this, generate like an actual image corresponding to it. So like it sees this and it thinks like, oh, it's a leather bag or a purse. Techniques like taking these like abstract plans for or abstract maps of showing like streets and intersections of streets and maybe like where streets are not, and turning those into actual images that would, you might expect to correspond to like if you're looking at something on Google. So like pretty amazing stuff. There's so much going on in this area. And it's almost always about images, and you evaluate it by looking at them and saying, that looks good. That's the only way you do it. Okay, so GANs. So pros are, these really are state of the art in terms of being able to generate from complex distributions. It's really like there's just nothing that compares right now. Cons are they are really tricky to train. But that said, like you've seen lots of examples where people figure out how to train them. So, and more research is going on to make it easier and easier all the time. But still, it's pretty tricky. And yeah, just lots of research going on. Okay, so we are out of time. I did have a couple more slides because someone wanted to see stuff on Siamese and triplet networks, but that person is not here today. And they're great, but maybe what I'll do is I'll fit those into something else that we're doing. The reason that they kind of appear is they're a little bit stronger than manifold learning. They're actually metric learning. So yeah, they also generate manifolds, but I think they're kind of different ways. I'll just leave it right there. So there you go. We're done. Happy to take any more questions or let's see, go.
Doing well, how are you?
Everything's fine, thanks.
Yeah, I mean, just so much stuff. The best thing to do